Well, thank you very much, William. It's a great pleasure to be here. Actually, I'll start to review quite briefly, some of the work I've been doing. Basically, almost all my career, scientific career. I started work on Helicity here in Santa Barbara 20 plus years ago. And I won't spend much time on Helicity, however, but just to give you an idea, forgive me, I'll be brief and probably you won't see much mathematics. I'd just like to present you several concepts I worked on, so it's focused on my own research, although in the title you see recent progress. I don't pretend to cover all the aspects, but I'd give you a flavor of what my impressions are on this field that is not young as it seems. It's 150 years old, as we know, and I'll focus mainly on magnetic fields, energy relaxation, and I'll consider the influence of the inflectional states on the diffeomorphism of magnetic fields, and then I'll show you recent results on ground state energy for the first 250 prime knots, and then some new stuff on lower bounds on energy. Then I moved to vortex dynamics. As I said very briefly, I'll just show you some results on torus knot solutions, and I'll touch upon a different topic, as in a sense is not so relevant to, say, knots, but has to do with complexity and structural complexity, and I'll move on to consider again a not theoretical approach to structural complexity in deriving, or at least showing you, a connection between the Jones polynomials for fluid knots and helicity. Perhaps not many of you know that behind the scene has always been Maxwell. Maxwell, it's amazing to read about the correspondence he had. This is a sketch of a braid done by William Thomson, and he addressed the question of how to detect braiding to Clerk Maxwell. This is a letter much later, 84. This is right at the beginning of the ether theory. This is a letter of Tate, moreover at the end of his completion, the 10 crossing table, where he asked to Maxwell, what about the composite knots? And then letters, of course, from Maxwell to both of them. This is to Tate. They corresponded a great deal over all the project of Tate's knot tabulation, wondering how to classify these objects, probably as webs. And this is going back 77, so we are at the heart of Tate's work on knot tabulation. You see already the overcrossing, undercrossing remarks coming up from these tiny postcards. There is a work in progress with Claude Weber, you may know Von, and this is a kind of a review of the origin of what we believe is knot theory and topological fluid mechanics. We know that Gauss is certainly at the origin of our ideas on knot theory. Applications to vortices came with a heater program of Kelvin that stimulated Tate. In between the two, there is a year that we should remember is 1858. In that year, Helmholtz published these papers on conservation laws. In the very same issue, there is proof that they were talking lunchtime. Very same issue, there is the paper of Riemann on the what we might call multiply connected domains. And indeed, have a look at the Riemann's paper. It's quite remarkable because it starts talking about the two-dimensional, we would say a two-dimensional flow with obstacles. And these obstacles, holes in the flow domain, are what we call the topological charges. Because then was inspired by the Kelvin's idea on circulation, etc., etc. Well, not yet, but that's 58. Quite remarkable. As I said, Maxwell is all behind this. If you have a look at what he calls, I think, preliminary chapter, have a read of that. It's totally devoted to multiply connectedness of fluid domains. It's amazing. It's 40 or something pages. he goes on and on talking about how to detect the topological complexity of the fluid domain and what is the relation between this complexity and the multivaluedness of potentials. All right, so we may say that this inspired what we may call now topological fluid mechanics. I will give you very briefly an idea of what I see as important topics in the fields. I apologize if, of course, I will forget something. This is evidently biased by my own interest. Knotted solutions is clearly a very important topic addressed by Kelvin in words, but very little has been done in terms of existence theorems. Anyway, the 3D fluid topology has an important role here. Vortex solutions in terms of topological complexity, the role of invariance, and the topological stability of these structures. You will see the word invariance coming up again in a moment. There are energy relaxation methods that have been suggested to investigate topology, and these are particularly well suited to study magnetic relaxations, in particular magnetic knots and links. Then while the energy functionals have been proposed, not by wild I mean not strictly speaking physically interesting, different may be power law in the Green functions, etc., but very, very interesting from a mathematical viewpoint to understand the limiting situations, etc., and the business of ground state energy. Then dynamical systems, I won't go into that, but we have a talk this afternoon by Daniel Peralta somewhere, and this is about existence theorems for vector fields, closed and chaotic orbits, explored numerically and not, yes, and Hamiltonian structures. You see again Hamiltonian structures, fluid invariance, and remembering not invariance. This is quite open question in mathematics, integrability, topology, etc. Then we have a change of topology. Of course, it's important. That depends on physical systems and through reconnection mechanisms. These might be ad hoc. However, if we, again, I invite you to think again of potential theory or asymptotic potential theory for example, filaments. In that case, I might see some generic features that are common to several physical mechanisms, i.e. the distance and the mutual angle of reconnections. And of course this problem is related to singularity formation that, as we know, is also an important topic in mathematics of hydrodynamics. Diffeomorphism of frozen fields is my approach to it. It is a very, very simplified view of fluid flow evolution. I would almost everywhere in this talk you will see ideal, incompressible, and perfectly conducting fluid that allows me to simplify equations a great deal. By incompressibility I mean divergence less of velocity, and the velocity is assumed to go to 0 at infinity. The governing equation, if you think of the magnetic field, for example, or vorticity field, the governing equation would be this transport equation that we recognize as a Faraday's equation for magnetic field, or Helmholtz equation for vorticity, with this assumption of div B equals 0. I take everything in L2 norm to have energy finite. From this transport equation, it's very old result. This is due to Cauchy, and we have this transport of the field at time t from the field at time 0 through this deformation tensor dxi dx 0j. So everything depends on this deformation tensor. So continuity, etc., etc. From this, we may immediately see, for some of us maybe difficult points, some others interesting points, i.e. pathological maps maybe that give rise to singularities. So if we assume that everything is continuous, smooth and differentiable, etc., we are in this context, and this establishes immediately an equivalence, a topological equivalence between the initial field and the final field. So typically you have these sketches of pretzel deformation. Suppose that this is like plastilin, and or a fluid structure. You can deform this to this, and you can show easily that by fluid, say, deformation, you can go from there to there. And there's a puzzle to everybody how to go there. This is taken from Prasolov, beautiful little book on applications of topological ideas. Of course, in going from here to there, you have a lot of twisting in the yellow stuff that is evidently not visible, and possible bifurcations when we have handles. So these are all unsolved questions. I remember to have organized a big program at Cambridge Newton Institute in the year 2000 that was parallel to the program of Arnold on singularities. And I can well see the relevance of this subject of singularities to problems in fluid mechanics. Well, the approach to fluid structures I use is, again, as I said, very, very simple. I'll assume a tubular neighborhood centered on the knot, taken as the axis, and circular cross-section, again for fluids, is if you like a strong assumption. There is no need to have a fluid structure a circular cross-section in its evolution. Anyway, the magnetic field will be embedded in this tube, and this tube is foliated. We take the magnetic field normal component equal to 0, so that is the surface, tubular surface is a material surface, and we can construct links in this way. This is, in a sense, is a manufacturing field. Volume and flux are conserved quantities in my approach, so we have diffeomorphisms that preserve volume and magnetic flux. Well, typically one important invariant of this center, last 50 years, is helicity. Helicity is just the dot product of a field times its curl, and was noticed to be an isotropy invariant by Whitehead, 1947. After that, it remained silent for a while until Voltier, in the context of hydrodynamics, showed that this quantity is indeed a frozen quantity in fluid evolution. And then Moffat in '69 established, in the context of vortex dynamics, a velocity, if you wish, you just take b velocity and a vorticity, the kinetic helicity in terms of Gauss linking numbers. And then the extra bit came from Santa Barbara's work, and then in Cambridge we just added the contribution from what we may call loosely self-linking. We might talk a little bit about this Calugariano formula. Just I mentioned it, I guess this afternoon, Mark.
Yeah.
There is a discussion on that. I call it in here. I just call it Calugariano-White formula. Sometimes it's loosely called the self-linking. The problem with that terminology is that Paul introduced it as self-linking as a geometric quantity. I'll say something just to warn you about that this afternoon. Okay, now in the context of ideal magnetic hydrodynamics, we consider these magnetic knots. Again, notice the cross-section is circular. The field may be decomposed as we would naturally think of to have twist of the field lines in an axial component plus a meridional component. And for simplicity, I will refer to this decomposition with this dependence on R only. And these are cylindrical coordinates. If we refer to fluxes, the poloidal and toroidal along the meridian and along the longitude, then the field I won't show you how to go from there to this, but the field can be rewritten in terms of fluxes. This is important for some variational approach to the problem of relaxation. And then we have the twist H, and this is just the ratio between the poloidal and toroidal. This H plays the role of reference helicity, or if you like, framing. Okay, we have a Lorentz force. First bit I'd like to emphasize on. This will be a little bit of geometry rather than topology, but it's interesting because it has implications in the topological approach to study of fields. So this is the Lorentz force naturally associated with the J cross B, with the presence of B field. Well, at the end it's just cross B cross curl B cross B. And if the really first order calculation gives you the information that the Lorentz force goes like curvature along the normal, principal normal direction. This force has been computed in appropriate orthogonal coordinates in a paper I wrote in 2005, so it's much more complicated than that. But the main issue here is curvature-driven flow, and this is an indication that if we have a change of concavity at one point in isolation, then the field line doesn't like to stay that shape, but to have an S shape in the plane, of course, is intrinsic. So this is just for visualization purposes. Intrinsic meaning that curvature equals 0 is a property of the curve in space, not necessarily in the plane. But what does that involve? Well, if we have an inflection in isolation, with Keith, we analyzed this situation here, and I presented this result at the conference at the time, so it was 1991, where you can find, you just Taylor expand your curve near the curvature equals 0 point, and then you find this generic twisted cubic where time here is purely kinematics. Well, you recognize this behavior going from one side to the other as a Rider-Master type move. And this, I talked about this a number of times to the solar physics community, and at a certain point, Trace 2002 showed this remarkable twist of an emerging flare on the solar surface, in the solar photosphere. Trace is a mission spacecraft that was sent then. Solar activity has a cycle, as we know, of 11 years. Now we are 2012, so we are about to see again, of course Sun is always active, but is particularly active on these peaks of 11 years time. So we are about to see again beautiful structures. As technology evolves, you see more and more details of these structures. These are plasma loops, of course. You cannot see magnetic fields as you cannot see vorticity field. You see tracers trapped by the field. I'll come back to these pictures because they are so beautiful. So because the magnetic field line doesn't like to stay in an inflectional state, it gets rid of inflections, then you're naturally led to think of knots without inflections. So a spiral knot, according to Adam Collins, is a knot free from inflection points in isolation. So we'll refer to spiral knots. As you go to a spiral knot and then braids, the minimum crossing number is that one, but the least number of crossings in an inflection-free configuration does go up, and that might be relevant for energy considerations. So any knot can be mapped to its closed braid representation. This is typical example of how you would transform a knot into a braid. And the work I did on inflectional states shows that a loose, not in a tight configuration, but a loose magnetic knot in inflectional state, it will get rid of inflections and is in actual fact in disequilibrium. It will get rid of inflections to evolve to an inflection-free knot. So as a corollary, we can see that inflectional knots are naturally isotope to spiral knots and braids. Well, this piece of work, I think, clarified or gave some grounds on the fact that on the solar observation don't show knots with particular intricate geometry, but knots with particular intricate geometry in the form of braids. And you see braids consistently. And except these looped, twisted flare that I showed you, they don't stay with inflectional configurations. So this is one of these beautiful pictures from the last active period of the sun. This is another one, and I use these pictures just to advertise the work I want to talk about that is quite important by Michberger on braid theory. So you see the resolution can get nicer and nicer, and we expect to see even more structures. I remember maybe 20 years ago, there was a lot of debate about if these were structures actually there or not, etc. Yes?
So if I have an arbitrary knot, I take some cabling in it, it's got lots of twists, then it's going to be inflection-free, but it's not going to be in braid position.
Of course, there are lots of possibilities to escape from. Yeah.
So, I mean, all these pictures don't show that, but I can imagine. Let me just leave it for that. You might.
Yeah, it's true. I also have reservation about the generality of that. I mean, remember, we assumed, I don't know if I remarked it, but we assumed the axial field much stronger than the meridional field, i.e. the twist contribution sufficiently low. You can go to the other extreme where the meridional field is very strong, then these won't apply at all. But of course the twist is relevant in this. Yes, Radmila.
Just a very simple question. So if inflection-free are preferred, does that mean that your braids will be on minimum number of strands?
Yeah.
Because then you cannot get the...
Exactly. Well, that's an interesting point. I would say yes, but there is no proof of this. Yeah, the number, because you go naturally to think of the minimal number of strings, and so to relate that to energy, I'll show you a little result later on this. Okay, magnetic relaxation. So magnetic relaxation is a context where you may do some simplified assumptions and see if you can get up with some analysis done, mathematical analysis done. We assume zero-framed magnetic links and components, all of equal flux as a start point. Then we have this important quantity. I use the half in front of this integral. This is magnetic energy. Remember, magnetic energy in this context is not an invariant, is kinetic energy as well. But magnetic helicity is invariant because of the zero framing. This simplifies to the form of linking between structures. So Moffat 85 and also Arnold, I must say, they talked about magnetic relaxation as a way to explore topology in the context of volume and flux preserving flows. So here we have all the ingredients. If we think of our trefoil knot, we have the Lorentz force, curvature force. And then we have volume conserved and flux conserved. So because of the Lorentz force is a shortening flow. So the fluid structure will lead to be shortened by the action of the force. As it gets smaller in average length, because the volume is conserved, it will increase in the average cross-section. And this will keep on until, of course, the surfaces, the magnetic surfaces, will touch upon each other, and topology will then stop, let's say, the relaxation. Well, of course, the natural relaxation would go on, and we don't know how to handle singularities, magnetic sheets, and reconnection of those. So that's why I will stop there with the analysis. And similarly for links. So there is a clear way to, at least as a toy model, to explore the effects of topology on energy on this very simple type of approach. So here I have collected a number of results from people in different periods. Essentially Arnold 74 and Friedman 88 worked on this relationship. And then Moffat 1990, Friedman Hay 91, and myself, well, they actually, Moffat 1990 and Friedman Hay 91 found basically this information, and there were two things left out, the constants basically. Here in this case, Arnold says, these should be a function of the geometry, of the size of the magnetic field. And here as well, because volume is constant, flux is constant, there was an uncertainty about the relationship between the mean energy and some topological information. In the case of Mike Friedman, they had the average crossing number here. And in the case of Moffat, in a Nature paper, he said that mean is proportional to some kind of topological invariant. You can, yeah.
Isn't a prefactor of the phi to the 6 over b, doesn't that just follow from dimensional analysis?
Well, I would say yes. I cannot remember, it's in Moffat's paper. I cannot remember, I don't think, so the phi, what is in Moffat's paper is based on dimensional analysis, the ratio between phi and v, not the constants, because the constants came from Friedman Hay's work on average crossing numbers. Here we see a third of this volume, so indeed is quite okay to put in relation the magnetic energy to some size of the volume where the energy would go if we allow relaxation to occur. But this first information doesn't say that much if we deal with topologies that have zero linking number, like Borromean rings, etc. Because
I miss this. The diagonal term in that helicity expression.
Yeah.
The diagonal term, if following what William talked about, I would expect there to be just the rise of the curves. Why isn't there a diagonal term in that?
Because we just simply assumed the linking numbers, self-linking number 0.
But so that means that the curves rise as 0? I mean, if I go back to the formula that you wrote down, then that would be the rise integral.
Yes.
Right.
But so, I mean, one way to think about it is when you cable these things, the self-linking, if you want, is a set of measure 0. So if you think of the tube, then it can have a ride or some invariant you can associate with it. But the way you do that is by considering pairwise all the cables inside the tube, and then that's many more of those than there are.
Well, I understand that term is small.
Yes.
But if you literally interpreted this formula, you would have ride, and so you're just going to assume that the curves have no ride with themselves. None of the curves have ride.
This doesn't say anything about that. But you would expect as obvious that energy goes up if you include self-linking. Different from 0. For example, an easy...
It's dimensionally smaller, so it's
that doesn't help. Okay. I mean, you're assuming all the flux is concentrated on a flux line.
Yes.
Right? And then you put it in that formula, but then you get the ride of the curve. Isn't that correct, Mark?
Not quite. Why not? Because the ride of the curve is only the expression of the parallel transports along the curve. It doesn't have any...
I'm saying if you put in A dot B, right, and B is the curl of A, and you say, I know where B is concentrated on this flux line, and I put that in the integral, I get the ride in the curve.
Well, you get the,
Yep.
the self-linking integral.
You have also twist, and the
Yeah,
two
twist as well.
the two might compensate each other.
The ride is typically only zero if the curve is planar. In these physical contexts.
Basically, you don't buy the point that it goes to zero.
Well, no, you can assume that the ride is zero. You get the Gauss linking number, you get the Gauss formula, except you put the same curve in
Right.
twice. Well, that's the ride of the curve.
Not quite, because it depends how you regularize these fields, right? Because if you've got this local bundle as you limit the local bundle of magnetic field lines to a single line, that's the self-linking. That's the ride is the stuff that's independent of the twisting of this local bundle of curves, and it's not quite. But what this theorem tells you is exactly how to take that limit.
Yeah,
my
correct.
interpretation.
So in other words, this is volume integral rather than integral of the curve itself. If you instead of volume integral you take integral of the curve, then you are right.
The ride is just the parallel transport residue of what's not the twist.
But if B is just a delta function, right, along the curve, right, so there's a direction, there's a delta function perpendicular to it, then that integral does become.
That would be but you've got to have the A, and what the A is doing, the A may have different twists, and so it's not just the ride.
Yeah, all right.
If you give it a finite thickness, then you have twistless.
A is not a regular procedure. You may do different things around this
Okay. All right, sorry.
We'll come back to that in the afternoon.
That's exactly the sort of thing I want to talk about.
So here we can say something about the minimum of the magnetic energy in terms of crossing number. Yes. Yeah? Oh, okay. Right. So you would be happy like this, because you would say, okay, we relate topology to the minimum of the magnetic energy, but we know that of course there are infinitely many knots with same minimum crossing number and different topology. So the question is to go deeper in that relationship. So we embarked in this project with a student of mine, Francesca Maggioni, following again a paper by Moffat and Chui. Anyway, the tubular knot is, as usual, taken as a cylindrical tube, but we used orthogonal curvilinear coordinates. By orthogonal, I mean exactly orthogonal. The metric is orthogonal. So pay attention to the papers when they use curvilinear systems, because very often this metric is not orthogonal. So there is, by that I mean, there is a compensating factor due to torsion that goes in the metric factors. If you use appropriate metric, then your analysis develops quite nicely. And the magnetic field, I assumed, is that one, and the flux and ratio for the twist parameter as that. Moreover, we kept the cross-section circular. We kept this fluctuating function psi tilde that you saw in the expression for the magnetic field in terms of fluxes as basically independent of arc length. And we also took the total length of your knot as independent from the internal twist. And then you can come up with a formula, a little bit of mathematics, but you can come up with a formula that is quite nice and tidy, written in this way in terms of this nice parameter, rope length. And rope length is convinced us that it's playing a wonderful role in this relaxation mechanism. So by rope length, I just simply here refer to the ratio in the tight configuration, the ratio of the minimal length of the tubular knot with respect to the radius of the maximal cross-section in the relaxed state. You see, this formula goes like lambda to the 4/3 plus contribution from internal twist, h. So h, as expected, if you start having twist internally, then increases the information, the energy content. So what we left to do is to resort to numerical work done by kind of relaxation algorithms, in other words, tightening procedures for knots and links. We started that using results by Sono, developed by the group of Piotr Pieransky, and then we went to Ridge Runner, developed by the group of Cantarella. This relaxation gives you information about lots of things. First of all, I'd like to remark that if you put on one single line all the knots belonging to that, say, 6 crossing or 7 crossings, that's why I put the bars over there, then you are in agreement with the relationship between M min in relation to C min. Because indeed the M min increases as we go up in the topological crossing number. But of course we know that, say, in this 6 class of crossing, there are 3 knots, and I can't remember, 11 probably in 7, and so on and so forth. So we go up in the number of knot types within each minimum number of crossing class. So we explored one by one these knots, and we came up first with this table. So this table shows you just the energy, the constraint minimum energy. Remember, constraint because we still have the cross-section circular, kept circular. And of course we have interstices as we consider tight knot configuration. So this might give further relaxation to energy. Anyway, if we plot the knots, the energy within each class of C min, say 10 crossings, etc., we observe this behavior. This drop in energy is due to the non-alternating knots, consistently. If we average out within each class, we resume the diagram of the parabolic functions. So we see that on average there is indeed this relationship between M min and C min. But what about if we just disregard this division in crossing numbers, and we normalize the energy to some reference energy, say the tight unknot energy. So we can come up with this information, zero twist now, and just a reference to lambda behavior. We see this kind of curve. So if you look at the best fit, we have this information. It's quite interesting because pay attention to this constant 4.5, because we then compare this plot with the energy for links. So we explore 250 prime knots, and then we go to links, and apart from some difference here, this looks the same, so it's quite nice.
How do you define, in this case, drop lengths for the link? If you have a link, then you can tighten to different parts in different proportion, and then you can obtain essentially any drop lengths you want.
I don't think so. I'm not quite sure, because how they do is done numerically, and the relaxation is done by how to say, perturbations on the local minimum.
In most cases, what is done numerically is they say most components have the same length.
Well, the same. It's not the same
Thickness,
thickness.
yes.
Same
thickness.
That might not be physically relevant.
Yeah,
that's say magnetic relaxation.
Yeah, but why would that assumption be relevant for your limit?
We just use the data. That's all. That's all we did.
I think you're right. For magnetic relaxation, there's no reason why the cross section should have the same.
No, of course not. Depends on the relative strength.
I just wanted to say, you can do this. There's another way of getting these shapes, which is you can take a knot, you could tie a knot in, say, a polymer or something, and you could throw it into a bath of colloids. And the depletion interaction will actually choose the knots that have the optimum shape.
So it works for links as well, just one component.
Okay, yeah. It's a conjecture that it works for all knots. It works for some torus knots, right? It doesn't, right? So I don't have any obviously you're doing it, but it seems to be very close to the idea of the tube the global thickness of the tube, right? So it wants to minimize the global thickness or maximize the global thickness of the tube.
As Dorothy's question is yes, that namely that you have a multi-component link is the reason why that colloid fusion process create equal thickness links on each component,
Moreover, it's fairly obvious that if you take link with, let's say, two rings of very different lengths,
Yes.
then they will come to very different thicknesses as a result of your colloidal strong.
That's right. So I don't know for links. I mean, I know it works for some torus knots.
Right, so we use two different approaches. One is based on a rather refined analysis on the field and within the tube, and the other was just an estimate on average stuff. This is the constrained energy. This is the formula that I quoted first by Moffat and Friedman. Hey, so you see, you have a possibility to relate the two. I mentioned the fact that having kept the cross section circular indeed means that there is a further there's a possibility of further relaxation for the magnetic field. Anyway, by relating these two information, we can establish a bound on the rope length, and the rope length turns out to be larger or equal to 2.66 C min to the 3/4, and that raises the question of the relevance of this power and then the coefficient, of course, in the remark of Rob to Paul Sutcliffe yesterday in Topological Charge went to the 3/4, and the 3/4 is a power that is appearing a number of times in a number of papers on relationship with the minimum crossing number. These so far, I don't know if you, Rob, may update me on this, but for any C min, this is 1.10, and for small C min, there are a number of results: Dan, Yao, Sullivan, Cantarella, Kastner, and Sullivan, etc. But for numerical check, this number is much higher. So it means that we did relatively well in terms of analysis, but in terms of probable realistic number is we are still a bit behind. For minimal braids, in the case of minimal number of strings, then we can apply this result by using Oyama inequality to relate the minimal number of strands to energy. So again, this might be useful to estimate energy contents from observation of solar structures or solar loops. Very, very important. Remember, 90% of the energy we get from the sun comes from the interaction of solar loops in the photosphere. So to have good estimates of energy is quite important for lots of reasons, especially under active periods of the sun, telecommunications, etc. For vortex dynamics, there is very little known, so we'd be very curious to hear from Danielle this afternoon to report on existence theorems. I mentioned existence theorems in the context of dynamical systems. Well, there are some solutions, very little from Kelvin's to now. In terms of numerical work, there are some information on knotted chaotic orbits, very little about stability criteria, a little bit more on invariance and fluid invariance and some relationship with Soliton invariance in the case of integrable Soliton equations and the Hamiltonian structures. So works here, I just mentioned a few. Kida was quite central in the search for knot solutions. Keener as well. I did some linear perturbation analysis on those. Berman and Williams, as we know, in dynamical systems for knotted orbits. And then some numerical work by Fuentes, and then the recent work by Enciso and Peralta Salas. In terms of direct numerical simulations of Navier-Stokes equations, Kida, of course, pursued the search for knots, and we have this very early visiometric analysis done by his group in '88, and then Aref and Zavascki in a Nature paper explored the linking of vortex tubes, and that's why I suggested Williams to maybe give it a try to see how close nature would be to this numerical simulation. It's quite hard, as we heard from William. There's instability immediately arising in these structures. I'd like to spend a word on LIA because it's a simplified form, the crude form for Biot-Savart. LIA is just velocity given by the curvature along the binormal instead of normal for Lorentz. So here we have a vortex filament. Basically, vorticity is just assumed to be a delta function on the thin cross section. And there's a very early work on well, we may not see a knot there. Is actually a non-knot wound around the meridional plane, but it's quite early work by Levi-Civita and his student Darius. Darius developed the LIA, as we call it now. And Levi-Civita, by the way, went in 1932 in a number of series of lectures also given in Paris. He went to studying the geometry of this shape in the meridional plane in great detail, and without realizing that was indeed the case of the Bernoulli elastica and the soliton that we call now Hashimoto soliton in vortex dynamics. So in a sense, this would go back to 1777, more or less. The equations turns out to be the same by analogy. And anyway, Kida worked on these torus knot solutions, so he found torus knot solutions to LIA, and the only little difficulty with these solutions that are expressed in the form of incomplete elliptic integrals, so you cannot do much in terms of simple analysis on those. So I consider linear perturbations on a circle, and in this small amplitude perturbation form, you can work out the solution nicely, and then you can move on to consider stability. So I have a kind of linear stability criterion that tells us something in terms of the winding number. I'll be quite brief here just to show you numerical simulations done by Barenghi's group on superfluid vortex filaments. Superfluid's code is quite trustworthy, because not only because it's by somebody who knows how to do it, but it's also because vortex filaments are consistently with LIA really thin. And so the approximation to Biot-Savart is a good one. Cross-section, I remind you, is Armstrong units, and the length is centimeters. So the aspect ratio is the right one to neglect the logarithmic contribution. So this is the torus knots tested. I have just, for an example, the 2-3. And at the time, they went on 15, 18 diameters, whereas if you reverse the winding number, you get the knot, as it propagates, unfolds, and the two parts, the inner part here, they tend to unfold, and reconnection takes place. So you cannot follow this. This was done in 1999, but it was redone recently by investigating lots of other properties with better code, and again, consistently we found this interesting result. We just looked for some properties, actually a number of properties. Here I just show you the writhing number against winding number, the velocity with respect to the winding number, and the relevance of topology with respect to unknots. So U denotes torus unknots. The standard coordinates are longitude and meridian. We see that knots with a very high number of longitudinal wraps tend to travel faster. We know that because we think of the vortex ring information is consistent with that. And we compared everything to the vortex ring of the average of the same average diameter. Just to have a clue, this helps also to model more complex structures with, i.e., vortex ring with twist inside. So considering one of these lines as an element of a more complex structure. I just touch upon complexity because it's something I've been working on in the last few years. So of course we all know that from the 80s that the vortex structures are very important and play an important role in the development of turbulence, and both in classical and quantized cases. So it would be nice to check some properties on tangles. So I again resorted to Barenghi, and then also the group in Tsubota in Japan and others confirmed the same results. We started to search for energy complexity relations on tangles, and if we consider this as a developed, mature vortex tangle with some isotropy, then we could look for information. This basically is energy and length, rescaled with some reference parameters, and this is the total linking number. The linking number, of course, flips and jumps because of the reconnection mechanisms, and the estimated riding number, the average cross section and estimated average cross section, and helicity. And you see this power law in the mature tangle suggests the relationship with energy that is of this type, and is quite interesting because it's so simple, and on the other hand opens doors to further investigation. Okay, well, since Vaughan was so kind to come, I had to talk about this. So relationship with Jones polynomials is a quite recent piece of work. Here we refer to helicity in this form. Well, suppose that vorticity is just along the tangent direction. So it's basically the tangent to the curve, and velocity is just say the LIA contribution, or also B O sub r, doesn't matter. But if we reduce this to a line integral, then we can write it in this form. We simplify further things in assuming that circulations is equal to 1 for every single component. Then we have this result. We took E to H. This is the heuristics in that is interesting, but my collaborator Xin Liu comes from high energy physics, from string theory, and so he has a flavor of the importance of these E to something in the search for these polynomials in the non-abelian Chern-Simons structures, and so we followed the same track. We took E to H as our variable, rescaled in somewhat, and you can show that it satisfies the skin relations of the Jones polynomials. I won't go into that, but is a rather long proof because you have to go one step by step to recover the skin relations, but it is rather simple work. The interesting fact, and I'm now not so prepared to answer your questions because it's new work and we have to digest it a little bit, is that we have to refer to some physical information. So tau, that is a parameter in the skin relations, plays here the role of E to H. So is in terms of helicity. There is lambda h of gamma plus. Gamma plus is this kind of thing. So we cannot avoid to have some reference field to start with, and this is our reference field. And lambda is a kind of uncertainty related to the way we estimate what we see. It can be this one or it can be in the other direction. So if we assume homogeneity of the tangle and assuming also that the same circulation for all knots and links, we can come up with this simplified assumption. Lambda bar is, say, a half, between 0 and 1. And this helicity of this structure, let's say a half k squared. It's just a simplifying assumption that allows us to relate, you see, this dummy variable to circulation. So my message here is that you would have these polynomials in terms of classifying detecting knot types with some accuracy. But then if you reinterpret this tau in terms of circulation, you have both topology and physics. You have the information from knot types plus the information, a little bit of information about circulation. So you have a function of these quantities. You go back to your blackboard and you do some calculations. These are just easy stuff, just elementary examples to show you how Jones polynomial would help you to say something also in terms of physical average, physical information of a structure. You can go on, for instance, the Whitehead link, etc. We are among mathematicians and theoretical physicists, etc. We all know E to X. The Taylor series for E to X might be important. I don't know. So we can do some further little analysis on that. So the future work for us, for Xin Liu and myself, would be to extend this approach to Vassiliev finite type invariants. We care about reconnection, so we wonder if it is any chance to have skin relations that incorporate reconnections, to have a kind of dynamical view of change of topology. We heard from Radmila, of course, the importance of Kovenov homology, so I want to learn something from her on that. And from another viewpoint, would be nice to ask people to implement, for example, Berenguer's group, Subota's group, etc., to implement this analysis on topological dynamics in an adaptive way, the predictive diagnostic of vertical flows in an adaptive way, when topology changes because of reconnections and all that. Thank you very much.
Substituting it e to the some thing into the variable and calling
Yeah. It's not that straightforward. You have to prove that skin relations arise by using e to h as a variable. So all the time you consider the cross-reaching. Then you have to compute the contribution in terms of right, etc.
So that's what I'm getting. So is that what's at the heart of it? You're somehow using the right relation to Helicity to...
Yes. To implement that in the local reconnection process, let's say. It wouldn't, technically speaking, it's not a reconnection. It's just a virtual smoothing of the knot crossing. So it's virtual, it's not real.
One question about this inflection avoiding behavior of the magnetic case. There's no analog of that in the viscous fluid case.
In the magnetic resistive case, you mean?
Yeah.
Well, I would expect there is. Well, it depends on the relative strength and dissipation rates. Yeah, no, I would say it persists. It's quite all right for solar loops because there we have Reynolds numbers that are astronomical. So it's still a kind of ideal magnetohydrodynamics, if you like. But for reconnections, I would say that it's still important. And for resistive or dissipative effects, it's still important. I can give you an easy example about that. It's boundary layer theory. We all know that boundary layer theory, so we're talking viscous, Navier-Stokes limit. Then the inflectional configuration of the profile against the body is quite important. It's triggering vorticity and all that. So the exact location of the inflection point and the exact geometry, the shape of the boundary layer, it's related to the development of vortical structures and vorticity production. So inflections play roles in physics, as we know.
Yes.
Yeah.
But in the case of an actual vortex knot in a viscous fluid.
Oh, for vortices. For vortices, well, curvature is equal to 0, and you have a binormal flow.
Yes. Yes, the effect.
So my remark about that goes in another direction. Sorry to distract you on another topic, but I would like you to notice that all the time we have reconnections in vortex dynamics, the resulting strands go in the binormal direction by curvature, and so they are even at the LIA level, even at this crude level of discussion, the reconnection mechanism is isotropizing the dynamics. That realization is very recent. It's just thinking about how LIA can be related to understanding local mechanisms. So it's not explaining anything, but it's just giving you a hint that all the times there is a reconnection, there is the children are born with high curvature, and if you have in vortex dynamics a flow along the binormal, high bent strands will move away fast from the plane of reconnections. So that mechanism goes on and on, because as they move away, they interact again. You have a new plane of reference. They move away from that plane of reference. So it's a very interesting, simple mechanism to understand how to isotropize dynamics and dissipation as well.